All right, yesterday we finished up talking about carboxylic acid derivatives, and we said that all of them are in the +3 oxidation state. We said the most reactive are acid halides, followed by anhydrides, esters, amides, and nitriles. And then we needed to briefly discuss the nomenclature for each of these, so we started off with acid halides. We said the best way to do this is to draw out the corresponding acid, so swap out the halogen for an OH, name the carboxylic acid, and then swap out the suffix for a YL, bromide, or chloride. So the example we had was hexanoyl chloride. Same thing with acetic acid. We popped off the ic acid and changed it to acetyl chloride. Anhydrides are a lot easier. If you've got a symmetric anhydride, you just replace the acid suffix with anhydride. And if it's non-symmetric, like in this case, you just break it apart into two carboxylic acids. And so in this case, it'd be acetic benzoic anhydride. All right, now we've got to jump into esters, which are a little bit different and more confusing. But I really want you to follow the same trend I've been teaching you. And I'll show you the generic trick. Is the first thing you always name is the group coming off oxygen. And then you want a space. And then you want your parent name next with an 8 suffix. So I'll give you an example. One of the more common examples in organic chemistry of esters. First thing you always want to do is look at that group coming off the oxygen. So right here we've got an ethyl group coming off. And then the next thing I always do is look at the carboxylic acid derivative. So in this case, if we think about this as a carboxylic acid, what is this carboxylic acid called? Close. Acetic acid. And if you think about this minus a proton, like that, this is the acetate anion. Does that make sense? So the 8 basically means that that oxygen either has a negative charge or is a part of an ester. So let's try to name this. First thing that always comes at the start is the group coming off oxygen. So it'd be ethyl acetate. So the main difference here is the ATE suffix instead of the ic acid. Does that make sense? Let's try one you might be more familiar with. Okay, so first thing you always want to do is identify the group coming off the oxygen, which in this case is a methyl group. And then if we think about the carboxylic acid, this would be what? Be meta nitro benzoic acid. Just like before, we're going to pop off the ic and the acid. So now we need to merge this all together. So this would be methyl space M nitro benzoate. Does that make sense? What people tend to get confused with is which to include first. The key thing to remember is always name the group coming off the oxygen first and then name everything else after that. It's easy to flip-flop them and think you need to name it the opposite way. Does that make sense? Want to try a harder one? Do one more. just like before, identify the substituent coming off the carbon. That's going to get named first. What would we call this group? It's not isopropyl. You could call it isobutyl because it has 4 carbons in there. Or if you ever forget how to name these, the easiest thing to do is start numbering away from your parent. So this be 1, 2, 3. You've got a methyl group coming off here. So you could call this a 2-methyl propyl. Tomato, tomato, most people would call this an isobutyl group just because it's easier to say. And then the other half of this is the carboxylic acid portion. What would this be called if it were a carboxylic acid? Butyric acid. So now when we merge this together, we would say this is isobutyl. Butanoate. Or butyrate. Either one would be acceptable for this one. Yep.
A little dumb, but does iso basically mean branch off?
Iso just means a branch off the very end. Yeah. That's one easy way to remember isopropyl and isobutyl is they both have that like chicken foot off the very end with two toes. Yep. All right. Now let's jump into naming amides. Amides are really challenging to name. All you have to do is change it to an amide suffix. So let's take an example. We'll compare the parent carboxylic acid to the corresponding amide derivative. So we've got acetic acid over here. And just like before, we're going to pop off the ic acid, and this will turn into acetamide. Does that make sense? So ic acid gets replaced with amide. There's also a few others that are pretty common. Let's try this one. Actually, I'm going to try to keep it consistent. We'll do the carboxylic acid over here, and then we'll do the amide on the right-hand side. What's the one on the left called? Formic acid. It's that smell of crushed ants, if you're into crushing ants. What would the one on the right be called? So we get rid of the ic acid, and this would be formamide. Make sense? If you notice, all of these, though, have hydrogens coming off the nitrogen. We can have amides where you have carbon groups coming off, right? So all of these were simple amides. Let's take a look at what happens with functionalized amides.
This is likely on the ACS.
This will likely be on the ACS. So just like before, we said this is formic acid. All right, this time what you have to do is indicate that there's a methyl group coming off that nitrogen. So in order to do that, you just say N-methyl at the beginning, and then you would follow with formamide. So that's an easy way of identifying what groups are coming off your nitrogen. The key is that N needs to be capitalized. A lowercase n means unbranched, not something coming off of a nitrogen. So you do have to be careful. Correspondingly, what happens if you have 2 groups coming off a nitrogen? This is a common organic solvent. What do you think this could be called? Yeah, in this case, you also want to double the N's, just like with numbering. So you do NN dimethyl formamide. So you do need to indicate, I've got a methyl group coming off not once, but twice off of the same nitrogen. If you have them coming off different nitrogens, quite often you'll see N and prime, and the prime just means that they're different nitrogens, not the same nitrogen. I'm not going to really push advanced examples like that. Most people, instead of calling this NN-dimethylformamide, simply refer to this as DMF. It's a very common organic solvent because it's very polar, and you can work with it pretty easily. All right, you want to try a challenge one? And then we'll be done with naming for a little bit. Okay, so for this one, first thing you always want to identify is the substituent coming off the nitrogen. So this would be N-ethyl, right? That's going to go first. Then what you can do is say, all right, what would the parent carboxylic acid be? And what I mean by that is, what would this be if it were a carboxylic acid rather than an amide? Let's try to name this. What would that be called? Yep, you want a number 1, 2, 3, 4, 5, 6. Got a methyl group coming off of carbon 5. So this would be 5-methyl hexanoic acid. All right, so now we need to merge these together. And like I said, you want to get rid of the oic acid and swap that out for an amide. So this would be N-ethyl 5-methyl hexanoic acid. Usually on the ACS exam, there's one or two that immediately don't make any sense. So, oops, sorry, hexanamide. Wow. Like I said, on the ACS exam, though, there's usually a few that have the wrong suffix or the wrong numbering system, so you can quickly rule those out through process of elimination. All right, that's pretty much it for naming for this chapter. There's a lot of new naming conventions, so if you are struggling with these, keep on practicing them. There's a lot of good practice problems in the textbook, though. All right, now we've got to talk more about carboxylic acid derivatives and their reactivity. At least one person's excited. And if you remember, for all of these, we had some sort of group coming off that position. So I'll just label that Z. And Z, if you remember, must be an electron withdrawing group in order for it to be a carboxylic acid derivative. And the key thing to remember is it is more reactive if Z is a good leaving group. So let's take a look at just that simple list again. So I'll do functional group. We'll look at Z. And then what I'll do is the pKa of the conjugate acid for Z in the next column. So we'll do the simplest one first. We'll do the acid halides. And I'll pick acid chlorides because they tend to be the most common. That means if Z pops off, it'd be just Cl minus. The pKa of the conjugate acid, which would be HCl, so it's Cl with an extra proton. This has a pKa of about -8, so very acidic. That means it's a good leaving group, right? That's a simple way to tell if you don't quite remember, is grab a pKa table. The next one be the anhydrides. So just like if this were to pop off, this time we're going to pop off that entire group. And if you think about the conjugate acid, what would the conjugate acid be called? Be acetic acid in this case. And acetic acid has a pKa of about 4.76. So you can tell anhydrides are a lot less reactive than acid halides. Acid halides are the king of carboxylic acid derivatives. All right, the next one that we have is with esters. And if an ester pops off, we have an alkoxide leaving group. That means that the conjugate acid would be an alcohol. What's the pKa of most alcohols? And I'll give you a hint. Water is an alcohol. About 15. So you can see it's not as good as the leaving group, not even close. And then below that, we've got amides, or if you think about an NH2 falling off, that is a terrible leaving group. In fact, we use amide as a super strong base when we deprotonate alkynes, right? And if you think about the conjugate acid, which would be ammonia, ammonia has a pKa of about 38. So this gives you a rough idea of the reactivity. The whole goal, though, is to kick off something that's a good leaving group during these reactions. All right, so let's take a look at just some super simple mechanisms. And this is called nucleophilic acyl substitution. And if you remember, an acyl group is something that contains that carbon-oxygen double bond, and all it's saying is we're going to swap off that leaving group for some other nucleophile. So if we've got a generic reaction, and I'm still going to use that placeholder Z, because we know it can be one of a number of leaving groups, and you react this with a nucleophile, the number one mistake I see students make is they say, oh, it's just like SN2 chemistry, like that. Why won't that work? What do you remember about SN2 chemistry? It only works on sp3 hybridized carbons, right? So this doesn't work using this arrow pushing scheme. However, what we can do is instead of immediately kicking it off, let's just dump those electrons up to oxygen first. Oh, that should be a Z. Now this oxygen has a negative charge. Now in this next step, we can kick this off. And just like I said before, the Z should be a good leaving group. That's what makes this entire process work. Does that make sense? The most important thing to remember is that you have to go through the tetrahedral intermediate in the middle, and Z needs to be a good leaving group. Let's make a note too that this reaction is more favorable if Z is a good leaving group. Does that make sense? All right, this first one though, do you think it's under acidic or basic conditions if our nucleophile has a negative charge? Basic, absolutely. So this first one we're looking at typically is done under basic conditions because you want your nucleophile to have a negative charge. Occasionally it's run under neutral conditions with a good nucleophile that's still negative under neutral conditions. Let's look at what happens under acidic conditions. Good thing is this reaction is pretty similar to the reactions we've previously seen. Typically under acidic conditions, you'll have some sort of acid source floating around, so I'll just write that as H+. And then you've got some sort of nucleophile, but because the nucleophile is under acidic conditions, it's very unlikely that it has a negative charge, right? So in the first step, what do you think happens? Protonation. Absolutely. So just like last chapter, you can protonate that carbonyl. now that that's protonated, your nucleophile is going to be really attracted to it because this has a major resonance structure now. Where that central carbon on the carbonyl actually has a positive charge, right? So this nucleophile is going to be very attracted to the central carbon. The nucleophile, after it adds in, though, typically has some sort of positive charge because it still has that proton on there. So what do you think should happen next? Yeah, I'd say deprotonate it. So I'll just write minus H plus. We'll deprotonate that protonated nucleophile. Okay, this looks pretty similar to what we were looking at before. We've got a good leaving group here. So what do you think could happen? Just like with the aldehyde chapter. Oops. That should be black dots. You've got lone pairs on oxygen. These lone pairs could help nudge that off, right? And kick that off as a leaving group. Kick off Z as your leaving group, and then last but not least, you can deprotonate your final product to get your nucleophile, or sorry, your final product as a neutral product. Does that make sense? So this general scheme can be used for a wide variety of reactions. All right, what I want us to do is actually work a little bit on our lab mechanism. So I'm going to give you some time to work on this in class, and I want you to check with your partner. And this is the mechanism that you did for making your ester. And when you made your ester, most of you started out with metanitrobenzoic acid. And you ended up making this into methyl metanitrobenzoate. What reagents did you use for that transformation in lab? Catalytic acid. What was the acid? Let's be specific. H2SO4. And what was the other part? Methanol. All right. So if we look at this set of reagent conditions, which pathway are we likely going to use? The simple basic one or the acidic one? Acidic. So what I want you guys to do is to see if you can draw the full mechanism for this using the acidic procedure that we had just covered. All right, just for the sake of time, let's try to start doing this as a class. What's the first step going to be? Protonation of the carbonyl. This is under equilibrium conditions too, so in this case, I am going to emphasize the equilibrium arrows. All right, now we've got our protonated carbonyl, we've got methanol. What will happen next? The methanol can attack in. Okay, so we're making progress. Now we've got two alcohols here and here. And then over here we've got our methyl group. And then we still have that proton off of the methanol. However, we can deprotonate it. I'm just going to shorthand this and do a proton transfer. And just write plus or minus H plus. And I'm going to move this proton coming off the methanol over to one of those alcohols. Let me actually slide this over a smidge. Okay, so now that we've done that, we've got a good leaving group. That's the Z. Normally we don't think of carboxylic acids as being good leaving groups. However, in this situation, if you protonate it enough, you'll have water as a leaving group. So yeah, it kind of follows that same procedure. And then in the next step, what happens? Yeah, in this case, the methanol, the electrons from the alcohol can clamp down and kick that off. Sorry, I chose the wrong side. And let me slide this over a smidge. Water is a byproduct here. So I'm just going to circle this and label that as a byproduct. / leaving group. And in the very last step, all we're going to do is deprotonate this. So I'll write -H+. So there's a lot of stuff going on in this reaction. A lot of stuff that's easy to overlook. The first of which is water is a byproduct and everything's under equilibrium conditions. Okay, so let's zoom out and look at the full mechanism. What do you think happens if you flood this reaction with excess water? It goes the opposite way, right? So that's actually a problem with this reaction. In lab, it said you need to have very dry product. If you start out with super wet product, the forward reaction is not going to be very favorable. So it does need to be dry. Ideally, you can even remove the water from the reaction mixture as it progresses and use Le Chatelier's principle to drive it to completion. The second thing is, if you look in step 1, we put acid in. In the middle step, we just did a proton shift, so no new acid, no new base. And then in the last step, we did a deprotonation. What does that tell you about the acid? It's catalytic, absolutely. So in this case, let's make a note that the acid is catalytic, which is why in lab you didn't need very much of the sulfuric acid to help drive it to completion. Yep?
So why couldn't it have been the ether that clamped down the scale?
It could have been. The reality is this is all under equilibrium. If that clamps down, you're not really going in any forward direction, and it would likely just result in a dead-end pathway. Yeah, it does get confusing, but you can go forward and reverse in a lot of these equilibria reactions. All right, this has a fancy name, so I did want to present it to you. It's one of the most famous reactions in chemistry. So this was conversion of a carboxylic acid. Oh. To an ester. Oh, wow. Using acid plus alcohol. This is called the Fischer Esterification. We're actually going to do this in our ester lab. The ester lab, I think we'll be doing in a few more weeks. But a lot of these esters, you start out with something like vinegar, very stinky. You react it with catalytic acid and an alcohol, and all of a sudden you can make it smell like pears, bananas, things like that. So a lot of the esters are very pleasant smelling. Does that make sense? All right, we're briefly going to jump into our next topic, which is the king of carboxylic acid derivatives. You can convert a carboxylic acid to an acid halide really easily in one step. And who remembers what reagent we needed to convert alcohols to alkyl halides? This is going back a while. SOCl2, exactly. So thionyl chloride was the one we used for alcohols. This also works for carboxylic acids. And if you remember, one of the reasons this works so well for alcohols was that you blow off sulfur dioxide gas, which bubbles out of solution, and then your byproduct is HCl. So it's this gas formation that really favors the reaction going forward because it's no longer in equilibrium when you're producing gas. So really quickly, let's take a look at the mechanism. This one's a little bit odd. So thionyl chloride looks like this. In the first reaction, it's typically shown like this, where the upper oxygen actually attacks the sulfur and kicks electrons over like that. Does that make sense? So you've got 2 electrons on this oxygen, 2 electrons on this one. So you got a big series of electron moves. Now we've got this intermediate. It's highly charged. Looks like this. The next step, we're going to kick off one of our chlorines. Like that. And we still have this chloride that got kicked off in that first step up there. And this chloride can actually act as a weak nucleophile, attack this carbonyl, kick up electrons onto oxygen. And I'm going to just move my chlorine down here. And we've got our alcohol like that. So that's one of our intermediates. Now in the next step, this oxygen's lone pair will clamp down. This bond will break, slide over like that, and we'll eject off the chlorine. So now we've got our parent group. Whoops. We formed SO2 gas in the process. We formed chloride in the process. And then last but not least, this chloride can steal a proton back. You end up with your acid halide, your sulfur dioxide gas, and HCl byproduct. Does that make sense? It's a pretty complicated mechanism, but like I said before, the key with thionyl chloride is the sulfur dioxide bubbling out of solution. Does that make sense? Quite often, this is run in a non-nucleophilic base to soak up that HCl, just to absorb all those protons. So quite often, a solvent that's used in this is pyridine. And pyridine is a great solvent because it's a good base but bad nucleophile. We don't want it to be a good nucleophile because we don't want it to substitute off the chlorine for a pyridine. We just want it to absorb protons, so it's commonly used in this reaction. Any sort of tertiary amine will also work, like triethylamine. All right, that's where we're going to stop today. Tomorrow when we come in, we're going to look at the reactions of acid halides. Try to get started on the pod too. The pod requires a lot of electron pushing arrows. I'm trying to get you to the point where you feel really comfortable predicting mechanisms just using elementary proton transfers and things like that.